All right, so I'm back, and I did say if I got 25 subscribers that I'd post a couple more solutions, and I didn't expect it to happen. That's a huge number, but it happened, so here we are. But yeah, thanks everyone for the comments on the previous video where I just went through how to solve these problems with Rust, like how to scan the input and things like that. And it was a bit of fun working through a problem. I will say that there is a live stream coming up with problem walkthroughs. So I'd say that'll be better than anything I can show you here. But I do have a few good ideas about how to solve a couple of these problems. And since it's just a practice session, hey, I'm here to help. So yeah, let's do this. So we'll just keep it brief, but I'll just go through a few highlights. So this first problem I'd recommend if you're newer to this kind of thing. Essentially, you just have to look at the last letter of each of these strings. So it's more about how do you scan strings, how do you get the last letter of a string, and then you also have to make sure you lowercase it because I think they're a bit sneaky here. They're like, oh, 3 to 20 letters, and here they're at most 100, which means it could be length 1, I guess. Length 0 would be kind of tricky, I think. So since the first letter is a capital, what if it's a capital Y? Sounds like a bit of a edge case. But yeah, I just made use of Rust to lower method. And then I used a nice match statement, which I quite like. So it's kind of like a switch statement, but a bit more powerful, I think. So the character, which is lowercase, we'll just get, so this is the last character. If it's a Y, then it's just nobody. If it's a vowel, then it's Alice. In other words, it's Bob. And then there's just a bit of formatting here. But whichever arm gets matched is part of this overall expression, and whatever that expression returns, this overall expression will return, and so it'll get mapped into this variable, and it's pretty efficient. Depending on what your match statements look like, Rust can turn it into like tables and things like that, so it can be constant time, which is nice. So yeah, I'd recommend that as the first problem. The next problem, I'll go through this one briefly. We already went through this one yesterday. And then I think Hex was the one that most people were asking for. Some people were messaging me on LinkedIn and things like that, asking me to how to do this one. But yeah, definitely recommend trying to do these yourself first. And maybe I'll try to provide a few hints and then, try to solve it yourself. And then I'll provide a few more hints and things like that. So this one, there is a physicist who's published some papers. Each paper has a certain number of citations, and we can calculate this H-index score based on the number of citations. So the H-index score of a researcher is the largest integer H such that the researcher has H papers with the least H citations each, which, I don't know, took me a little bit to get my head around that sentence. So probably pause and just think about it for like 30 seconds. But yeah, and there's quite a lot of data here. So there's 100 test cases, and each case can have up to 10 to the 5 papers. So it's quite a lot. So for that, you kind of want ON or maybe N log N. I couldn't think of a ON way to solve this. But if you want to try, I know there's some trick for range minimum query, which is close to constant time, and it uses like union find in a stack. And then there's another trick for selecting the k lowest numbers from a list in constant time, at a linear time, sorry. And it calculates the median. There's like an algorithm that can get the median of a list of numbers in like just constant time, basically. It's kind of a big constant, but it's constant. And yeah, the way it selects the k smallest numbers is kind of using the medium and then kind of divide and conquer and things like that. But yeah, it's definitely a bit beyond me. So I just went with the n log n solution. Um, so how did I think about that? Well, I guess going back to that definition of what the H-index is, it's basically, I guess initially, like let's say you're trying to maximize your H-index. Initially, you want to publish lots of papers because your H-index can't be larger than the number of published papers you've published. But then at the same time, you need lots of papers that have lots of citations. So as your H-index increases, the only way to increase your H-index is to have more papers than what your current H-index is, and so of papers of which have citations that are larger than your H-index. So it kind of leads us to think, we want to track the papers with the most citations. And if a paper has, conversely to that, like if a paper has less citations than our current H-index, then it can't improve our H-index anymore because the H-index only counts papers that have, a citation count equal or greater than the H-index, and you need H of them. So we kind of have to. So this is the first paper published, and the second paper published, and so on. And then this is the H-index. So it's 1 and then 1, and you can see it slowly going up as they get more papers that have more citations. So it's kind of like, okay, maybe you want to track the papers with the most citations and just remove the ones that don't have as many citations as our current H number. So I'll just briefly go through this and then we'll go on to the next problem. But yeah, maybe you want to pause it now and just try to solve it yourself. And if you're going to do that, well, I don't want to give too much away, but in terms of data structures you could use with C++, multi-set would be nice. Whereas in Rust, there's no multi-set, unfortunately. But there's quite a fun exercise to try and implement one yourself, and you can use the B-tree map, and I guess you use as the value, like, a vector, or you could just use an integer count. You just have to be careful with duplicates. So that's actually what I did. But then I realized after doing that, I could have just used a heap, and that's pretty much like a multi-set, because it turns out we're only concerned about of the papers that have more citations than our current H-index, which is the one with the least citations, because that's kind of what's kind of restricting our H count from increasing is what is the paper with the least citation of those, and also how many papers do we have with that many citations or more, because those are the only ones that contribute. So I think it's probably a bit of a mouthful, so just write it down here. And what are we trying to get as well? We're trying to get this. It's always helpful to have the answer on hand to make sure you're doing things correctly. So if we start off at the first one, then let's just use a multi-set or like a Rust B-tree map. But I'll just assume that it allows you to do multiple entries because it'll just make it easier to see things. So we'll put the 1 in there, and our H value will start off as 1. And you can already see we've got the correct answer. So after the first paper, our H-index is 1. And then we have a 3. So 1, 3. But then this 1's no longer useful because it's not bigger than our H value. So we can just pop that. Let's just say it's a heap. Anyway, so our H-index is still 1 because although we've got a 3, we only have, so we've got one paper with lots of citations, but we've only got one of them. So whereas once we get the next 3, then all of a sudden we've got 2 3s. So our H-index goes to 2 because we can see by the length of this data structure. I guess you have to be careful how you count how many values you have in it. It might not be the length, it might be the sum of all the keys. So, but you need to be able to access it in constant time. But so we got, although we've got some 3s here, we only have 2 of them. So the minimum of 2 and 3, the minimum of 2 and 3 is 2. So our H-index will just be 2. And then we have a 2. There's this 2 up here. We've just calculated 2, which is the first 2 over here. The 2 isn't going to do anything. Like we could add it in here, but we know that 2 is never going to help increase our H-index. So we'll just, this will stay at 2, and it's the same again. And then we get this 15. So now we've got 3, 3, 15. And so that's, now we've got 3 numbers of size 3 or higher, and the minimum of 3 and 3 is 3. And so we'll just, so H will be the, at each step, H will be the maximum of the minimum of the size of this data structure and the minimum value of this data structure. Oh, yeah, so I think that's that question done. So let's go to the hex question, which everyone was asking about. So yeah, apparently this game here was invented by, I don't know who this person is, but John Nash is like this famous Nobel Prize winning economist. And like apparently when he got a reference to his PhD at some university or something like this, his reference was just one line saying he is a genius or something like that. And so he got accepted into the school, and that's where he came up with the theory of game theory, which is a pretty cool. I mean, I did one economics paper at university, and I mean, they let me skip some other economics papers and just do this interesting one, which was coming from a math background. It was reasonably straightforward, but quite interesting. And then, and sorry, kind of going on a tangent here, but with game theory, you have a whole lot of players that are playing a game with optimal strategies, and each player has a list of strategies available to them. And based on the strategies, each player knows every other player's strategies as well. So you kind of have like this matrix of like players and strategies. And each, it's kind of like, okay, what will everyone do? Like, so everyone will basically optimize. So based on each player's strategy and the other, based on what strategy a player chooses and what strategies the other players choose, then some kind of action will occur and you'll get some kind of outcome. And each outcome has like an expected utility for each player. And so each player will try to optimize their utility. And so John Nash came up with this concept, and he found this thing called Nash equilibrium, which it's like, say there's a certain outcome, and for a certain player they could change from one strategy to another to improve their utility. Then they will change strategy, but then everyone else will see that, and they will see like, oh, what if I change my strategy? Maybe it increases my utility, and so then it'll go to a new equilibrium, and it keeps going, but eventually it converges somewhere, and then no player can change their strategy to improve their outcome, and so that's called the Nash equilibrium. And even though sometimes it's like at the demise of everyone, because everyone might try to screw each other over, like if they all collaborated, maybe it would be a better outcome. And there's something called like the prisoner dilemma, which is like, it shows this. But yeah, anyway, it's an interesting an interesting thing. So I'd definitely recommend doing some game theory if you ever get time. So in this game, we have like the n times n board, and you can see each player takes turns at placing a piece, and they want to connect their ends. So blue wants to get a line. So you can see blue's won this game. They've connected a line from the left side to the right side, whereas red was trying to connect the top to the bottom. And we get given a game board. So you can see, yeah, like the game board might look like this. So it's an n by n board. And we have to work out, like, does nobody win? Does blue win? Does red win? Or is it impossible to get this game board? So because the players take turns, I mean, if one player has way more pieces on the board than the other, then clearly they weren't following the rules and taking turns. So if they're not taking turns, then it's impossible. But another thing is, one that was quite interesting and caught me up the first time was this one. So this is impossible, even though they've both been taking turns. And you can see here, I'll give you a second to think about why it's impossible. It tells you here, impossible. But basically, blue has one line going across, and then they've done another line going across. And the rules of the game is that once one player gets a line, you end the game there and you stop. Whereas it looks like they've kept playing, and so now blue's managed to get two lines going across. And so I think that's kind of the crux of what makes this problem difficult is how do we know that they, like, if there's a winner, how do we know they didn't stop playing on time? Like, how do we know it's an impossible configuration? And in these kinds of situations, and in game theory, it's often good to work your way backwards and think, okay, well, what was the last? If blue won, they must have placed the last piece. That's another edge case to watch out for. Is that if red has more pieces than blue on the board, but blue won, that's impossible. But let's just say blue has the same or one more piece than red, and blue won. What was the last piece that blue placed? And I mean, there must be a piece of blues that we can remove such that blues left and right sides are no longer connected. And that would be a candidate for the last piece that blue placed. And that means it would be a valid configuration in blue ones. But because we have 100 of these boards and each board has 100 squared cells, then that's 1,000,000 different cells and throughout the test cases. So we've got to be a bit careful about efficiency, because if we figure out, let's say we find red ones, or let's say we find blue ones, and then we want to try removing a cell. It's like, so we have a million, and then we're trying to remove 1,000,000 cells, and then like do it all again to see if it's still connected. Then it's like you're trying to remove all these different things, and then you're trying to do all these different paths each time. So it's going to be too slow. So yeah, so it might be easier if I just draw a few diagrams about how to think about this. Let's clear this. Okay. So if we just have a line going from one end to the other, it's fine. And if we had that, it's fine. Like, we could remove any of the cells along here. Whereas, and even if we had like a kind of X kind of a shape. So if there's a single cell here, then this is valid. We could that's a single piece that we could remove. Whereas if we have something like this, let's just say these are all blue tiles. We won't bother drawing the red tiles on here. Then no matter which tile we remove, I mean, there is no possible last piece that we could have placed. We can't remove a piece. So how can we write some code that figures out that there's more than one path to the end? Because when we saw the X shape, there was more than one path to the end, but that was valid, whereas sometimes it's not. And imagine this graph could be quite complicated. So I think you can use depth first search, although I didn't use depth first search. I'll get to how I did it in a sec, and I did it a different way because I thought it would be fun and a good way to try something new with Rust. But I'm thinking you can use depth first search. So I think this is probably the way you're supposed to do it. So let's say this is, let's just keep it simple and just say it's like this. And let's say, oops, I didn't want to make that black. It's kind of new to this drawing tool. Yeah. So let's say you found this path. And if you use depth first search again, how can you check if there's another path? Because you might come along here and be like, oh, well, this is blocked. So there's only one path. And I mean, I'll call this like an H shape. And remember at first I had like a Y shape on there. So a Y shape was valid, whereas like and an X shape is valid as well, whereas like an H shape is not valid, and so on. So what I think you could probably do is after you do this depth first search, you delete all of these edges. And yeah, I'll get into it like what is an edge, what is a node and things in a bit. Basically, we can think of each cell as a node, and an edge is each of, since they're hexagons, each of the 6 sides that the hexagon's connected to. But yeah, I'm just drawing lines for now because maybe it's easier to think about it at a high level. Oops. So if we delete all of those edges, then when we get to here, this edge is no longer here. But because these are bidirectional edges, if we have one edge going down and one edge going up, then although we can't go down this way, we can still go up this way because we haven't deleted that reverse edges. So we could go up here and then we could go across. And then we can be like, okay, well, of all the left-hand nodes, there's 2 paths to the possible right-hand nodes. And so that makes me think that it's not possible. That's invalid because there's more than one path across. And I think that would be efficient enough because it's just 2 depth first searches or breadth first searches. Another thing you could do is, if that doesn't work, is after you've found this path, you could delete all of these nodes and then put them into like one super node, and then perhaps every edge that's connected to any of the nodes that are within the super node could then connect to the super node instead, and then you could run depth first search again. But I solved this with max flow, and so just give a bit of an overview of that because I think it's quite a fun way to solve this. And so you remember yesterday in the video, I showed you that there was this scanner. So I'm not sure how to pronounce this, Kenko. But yeah, she's written some really nice code. So so the scanner has been really useful. And then I saw she also had a max flow algorithm, which is nice. And max flow, I guess you could think of it as like pipe of water. It's from like a source node to like a sink node. And so you have a certain amount of water coming into the system and a certain amount of water exiting the system. You could also think of it as like current or like electricity. But if each pipe has like a capacity of like 1 cubic of water per second, let's say, then at each junction of pipes or each node, the amount of water coming into that junction has to equal the amount of water coming out of the junction. And if you have integer edges, then the maximum flow, like if you have integer capacities, then the maximum flow from one end to the other will always be an integer, which is quite interesting. And so yeah, I'd recommend going through this code. It's really cool. And you can look up maximum flow on Wikipedia. But how does this help with the problem? So if we have, let's say we have some kind of complicated graph. Let's just say it looks like this. So if we drew a source node going from here and a sink node over here. So let's say we're pumping water through the system and we say, okay, what is the bottleneck? Well, the bottleneck here is going to be this. If all these pipes are capacity 1, then the bottleneck will be this pipe in the middle, because every piece of water has to go through here, and it's capacity 1. So that's a bottleneck. That means our flow is only 1 through this system. And if we cut this system in half, like let's imagine the cell that is here. So since we know that there's only one cell that intersects this line, then that means we could remove that cell, and that's what we were looking for. So yeah, if the max flow is 1, then we know the bottleneck is of size 1, and that means we know that there's one piece that we can remove. Whereas if there were more lines coming across here, like if it was 2 or 3 or so on, then we know even at the bottleneck, we'd have to remove 3. And so there's no way we could remove 1. And so what is the efficiency of this? So the way max flow works is it does a depth first search to one end, and then it tries to do another depth first search, and each time it tries to add water wherever it can. And as it can't add any more water from one end to the other, then it starts to reverse water from some edges until it finds another way to add water. So it's kind of an interesting algorithm. And the complexity is equal to the number of edges times the maximum flow. But for us, we only need to know if the flow is 2 or higher, right? So we can restrict this F max to be no greater than 2. So that means the efficiency of our algorithm will be equal to twice the number of edges, which is pretty quick. The number of edges is just equal to, well, each node only has 6 edges. So it's well, the way we implement it, it'll have, I think, 12. Well, I think we'll have, let's say it's 100 squared nodes, but we're actually going to have around 2 times 100 squared nodes, and I'll get into that. And then each one will have maybe like 6 edges or something. So yeah, it will, basically I ran this on the max case. I created the max test case, this here, and it ran in 0.2 of a second, so it was pretty quick. And so that's doing 100 different graphs of 100 squared size. So yeah, it's quick. And the implementation was nice and easy because I just used that beautiful code that this person's created. So how, I guess first of all I should say, how do we constrain it to 2? For that I just added a source to the source, and whenever you create an edge, you have to say what the capacity is. So I just made this capacity 2, and I also made the capacity um, here 2 as well. So I had sync, and now we know the maximum flow will be no higher than 2, and so it won't have to do many depth first searches, and so it'll be efficient. Whereas otherwise, I think you can have up to like E or E squared um, depth first searches or something like that, which let's just see. Yeah, I think E squared and uh, so for us this will be put. And one thing we have to be careful about though is how do we make sure we only flow through each cell once? For example, let's look at this point. Let's look at let's just say there's another edge here. So let's say we've got like this X shape here, right? So I'll delete everything. So let's say this is our hexagon in the middle here. And these are all capacity 1, let's say. So then we could have something that comes through here, and another one that comes through here and through here. So that means we have a flow of 2 going through this node. And that's not good because you can only use each cell once. You can only place 1 piece in a cell. So to get around that, there's like a cool trick that you can do. So I'll just use some circles to represent um, the hexagons. So let's just say, and we're only concerned about blue hexagons, so there could be more 6 hexagons around this, but let's just say there's only 2. Easier to draw. And I've made these 3D, otherwise these wouldn't be very good circles. So I guess you call this isometric drawing. But what we can actually do is represent our cell as an edge, and then we can add a capacity to it. That's quite cool, and that's how we can restrict the flow through a cell. So instead of each cell being a node, we'll have each cell as an edge with a node that represents the input to that cell and a node that represents the exit point of that cell. And then we have a one-way edge, so not a bidirectional edge, just a, I guess you call it a unidirectional edge through it. And that will make sure there's only one thing is using that cell. So that's quite cool. So these will also have, oops, how did I draw an error? So these will also have edges. And then we connect these up like this. Because these are neighbors, then we can flow from our exit point to the entry point of our neighbor. And this gets a bit messy, but I think you get the point. And so let's say this is the left side of the board, then our source would be going to here. And then we'd have that other super source, which is of capacity 2. Let's say this is the right hand side, then this would be going to here. Oops, sorry, that's a mistake. This should be going to here. This should be going here. And then we have that other one of capacity 2. And I mean, I guess actually this we only really need one of capacity two. If this was capacity two, then I don't think this can be higher than two, and vice versa. But I just made both of them capacity two because why not? So yeah, it's pretty cool, and so it all seems pretty complicated, but by using that algorithm from the GitHub repository that we found, I was able to implement this probably more easily than if I'd just done depth first search myself. Um, and I mean, if you want to save some time, you can like use some helper methods to make sure you have reusable code so that when you do this for blue, then you go for red at the same with the same code. And yeah, I also had a helper function for these. If we look at this code, there's like an add edge method, and it only takes single like usize numbers to represent the nodes, whereas we have cells with like an ij value. So I hashed the cells. So for example, cell ij, I'd map to I times n plus j. So that gives us a number from 0 to n squared. And so for the end node, I'd use that. And for the out node, I'd use I times n plus j, and then I'd add n squared to that. So my range from 0 to n squared is the n nodes, and my range from n squared to 2 times n squared is the out nodes. And then add a couple of extra nodes at the end, which were like the source, the super source, and the sink and the super sink. And yeah, it was super easy to use. I mean, there's an example of how to use it. You just create a new struct with the number of nodes you want. And then for each edge, you just and capacity, you just add it, and then you just run that, and you're done. Bob's your uncle, well. So yeah, that was cool. And I guess it can be a bit messy because each cell has 6 edges. So what's a good way to add edges? So I thought I had kind of a nice way of doing that. Let's see if you can see this or not. Maybe I have to move this. I don't know how to resize this. It would be nice if I could drag this across. Yeah, I'll drag this into here so you can see this. What did I do? Yeah, so I had an in hash and an out hash helper, which was cool. So those are all the capacity one edges I showed you. So each cell has like an edge, which is this, and then for each neighbor, so I go from 0 to n and then 0 to n minus 1. So if you know if my cell and the cell to my right are both equal to the character I'm looking for, then I just add an edge. I made another helper here, so I just add that, and this uses the same hash helper. And then I also look at the one above and below, and then there's the other edge as well. So I look at yeah, like the current cell, and you go up one and then one to the right, and that's kind of like uh, let's see if I can find it. Yeah, so it's like say I'm here, I'm going I minus 1 and then j plus 1, so I'm going across to here. So for every pair like that, I'm adding the edge. So I thought, yeah, that was kind of a nice way to do it. What else? I think that's pretty much it. And I just had some logic. So I just checked the flows. If it's 2, then it's impossible. This logic could definitely be tidied up a bit. But yeah, that's pretty much it, I guess. So yeah, feel free to comment on what approach you think's best, and if you had any tricks that reduced the amount of code that you had to write, or if you know any other ways of solving these problems. Especially if you had like a linear time approach to the second problem, I'd be keen to hear how to do that. Um, I, yeah, I was trying to figure out, and then I was just like, I don't have time for this, so this it's easy just to use a heap. But yeah, anyway, enjoy your day and enjoy the rest of the competition, and yeah, definitely check out the live stream, which will be, when is that? February 18th at 3 o'clock UTC. So I'm looking forward to that, seeing how they do it. And they often have proofs of like why the answer is correct and things like that. So it's interesting to see the logic they use and things. So yeah, um, I'll see you next time. But I think for future videos, I'll probably focus more on Rust and doing little projects. I don't know. I've got a couple of algorithm type problems I could go over. Like there's a Kaggle contest I did, so I got an interesting solution to that. And uh, I had some interesting solutions to a few other like Google Code Jam problems and Facebook Hagercut problems and stuff in the past. So maybe if you guys, if everyone's came for it, let me know, and maybe I can make a few videos on those. Otherwise, I might do some other kind of rough projects like making little web apps or something like that, and I might do a bit of TypeScript and Angular and things like that, and some GraphQL and MySQL and things. So we'll see. Just yeah, if you have any ideas for videos you'd like, feel free to suggest. But yeah, thanks a lot for watching, and have a good day.